Earth experiences massive cycles of freezing and warming roughly every 100,000 years. During these periods, known as ice ages, glaciers expand across continents, sea levels drop, and ecosystems are profoundly altered. These cycles are not random. They are caused by precise changes in Earth's orbit and axial tilt, which affect how much solar energy the planet receives. Evidence of these ice ages is recorded in rocks, ocean sediments, and ancient air trapped in ice, allowing scientists to study the timing and extent of past climate changes. But why does Earth enter these regular periods of extreme cold? Earth's ice ages are periods when enormous portions of the planet became shrouded in thick ice, glaciers spread across continents, and global temperatures dropped dramatically for tens of thousands of years. These periods are not just brief cold spells, they are extended episodes in which Earth's climate undergoes profound shifts, reshaping landscapes, oceans, and life itself. Understanding why these ice ages occurred, why they repeatedly returned in cycles, and what forces drove them, requires a careful look at Earth's climate systems, its position in space, and the delicate interplay of factors both internal and external to the planet. The scale and rhythm of these icy epochs are staggering, involving changes that happen over tens of thousands to hundreds of thousands of years, leaving marks that scientists can read long after the ice has retreated. During ice ages, the Earth's climate system behaves in ways that are both subtle and massive. Small changes in temperature, precipitation, and ocean currents can set off feedback loops that amplify cooling, allowing glaciers to expand and ice sheets to grow. These ice sheets are not static. They move, flow, and grind across the land, reshaping mountains, carving valleys, and leaving behind deposits of rock and sediment known as moraines. The pressure of these ice sheets is immense. Thousands of tons of ice pressing down on the land over thousands of years can even depress the Earth's crust, temporarily lowering regions beneath sea level. When the ice finally melts, these areas slowly rebound, a process that continues today in places like Scandinavia and Canada. The evidence of these past ice ages is everywhere. Glacial grooves etched into bedrock, massive boulders carried far from their original locations, and layers of sediment that record the advance and retreat of ice over time. The timing of ice ages is not random. Over the last million years, Earth has experienced ice ages roughly every 100,000 years, a pattern that corresponds to slow changes in its orbit and tilt. These cycles, known as Milankovitch cycles, involve small but significant variations in the Earth's orbit around the Sun, including the shape of its orbit, the tilt of its axis, and the wobble of that axis over tens of thousands of years. When these orbital changes align in particular ways, they affect the amount of solar energy reaching the Earth's surface at different latitudes and seasons, triggering the growth or melting of ice sheets. For example, when summers in the northern hemisphere are cooler, less ice melts each year, allowing glaciers to expand gradually. Conversely, warmer summers can lead to the retreat of ice and the transition into an interglacial period, a warmer interval between ice ages. These orbital effects, while critical, are only part of the story. Feedback mechanisms within Earth's climate system amplify or dampen these changes. One of the most important feedbacks involves the reflectivity of ice itself. Snow and ice are highly reflective, bouncing sunlight back into space. As ice sheets grow, more sunlight is reflected, further cooling the climate and promoting additional ice growth. Conversely, when ice retreats, darker land or ocean surfaces are exposed, absorbing more heat and accelerating warming. Another powerful feedback involves greenhouse gases, particularly carbon dioxide and methane. During ice ages, atmospheric concentrations of these gases drop, contributing to cooling. When ice melts, greenhouse gas levels can rise, reinforcing warming. These feedbacks create a delicate balance in which relatively small changes can trigger large swings between glacial and interglacial periods. The effects of ice ages on the planet and life were enormous. Ice sheets covering North America, Northern Europe, and parts of Asia altered weather patterns, ocean currents, and sea levels. Global sea levels fell by over 120 meters during the peak of the last ice age, exposing land bridges such as the one between Siberia and Alaska, which allowed humans and animals to migrate across continents. Rivers and lakes shifted their courses as glaciers redirected water, creating new habitats while destroying others. In many regions, cold and dry conditions led to the expansion of deserts, while in other areas, tundra landscapes replaced forests. Flora and fauna adapted to these extreme changes, with species either migrating, evolving new traits, or facing extinction. Humans, too, faced enormous challenges, developing new tools, shelters, and strategies to survive the harsh Ice Age conditions. The record of ice ages is preserved in layers of ice and sediment, in the chemical composition of ocean sediments, and in the fossil record. Deep within Greenland and Antarctica, ice cores drilled from kilometers of ice reveal annual layers, trapped air bubbles, and isotopic signatures that allow scientists to reconstruct temperature, precipitation, and atmospheric composition going back hundreds of thousands of years. Similarly, the ocean floor preserves microscopic shells of plankton called foraminifera, whose chemical makeup changes with temperature and ice volume, providing a record of glacial cycles over millions of years. By studying these records, scientists have identified not just the timing of ice ages, but also their pace, intensity, and impact on global climate and ecosystems. The patterns of ice ages are also influenced by the continents themselves. The positions of land masses affect ocean currents, wind patterns, and the flow of heat around the planet. For example, the formation of the Isthmus of Panama around 3 million years ago redirected ocean currents, strengthening the Gulf Stream and contributing to the onset of the current cycle of ice ages. Similarly, the uplift of major mountain ranges, such as the Himalayas and the Rockies, altered atmospheric circulation and increased weathering of rocks, which removes carbon dioxide from the atmosphere and promotes cooling. The interplay between geological processes and climate creates a complex system in which small changes in one component can ripple through the entire planet. While the most recent ice age cycles have occurred every 100,000 years, Earth's climate history includes periods with very different rhythms. In the past, ice ages have been triggered by a combination of factors, including changes in solar output, volcanic activity, asteroid impacts, and the slow drift of continents. Some ice ages lasted tens of millions of years, covering nearly the entire planet with ice, while others were more regional in extent. The so-called snowball Earth events, which occurred over 600 million years ago, may have encased the planet almost entirely in ice, creating extreme conditions that forced life to adapt in remarkable ways. Understanding ice ages also requires looking at the cycles within the cycles. Even during an ice age, the climate is not uniform. There are warmer and colder phases, often lasting thousands of years. These shorter cycles, called stadials and interstadials, are superimposed on the larger glacial and interglacial rhythms. Scientists have found evidence of abrupt climate changes, sometimes occurring within decades, that show just how sensitive the climate system can be. The causes of these rapid changes include shifts in ocean currents, sudden releases of greenhouse gases, or large volcanic eruptions, all of which can tip the balance of climate and trigger dramatic transformations. The human story is deeply intertwined with the ice ages. The last ice age, known as the last glacial maximum, peaked around 20,000 years ago. At that time, massive ice sheets covered much of North America, Northern Europe, and parts of Asia. Humans lived in scattered populations, adapting to cold environments with specialized tools, clothing, and shelters. As the ice began to retreat around 11,000 years ago, humans migrated into new areas, domesticated plants and animals, and laid the foundations for civilizations. The availability of fresh water from melting glaciers, the expansion of fertile lands, and changes in animal populations all shaped human survival and cultural development. Ice ages did not just shape the planet physically, they shaped the course of human history. Modern science continues to uncover new details about ice ages. Advances in technology allow precise measurements of isotopes, detailed mapping of ancient ice flows, and sophisticated climate modeling that can simulate past glacial cycles with remarkable accuracy. Researchers study ancient sediments, fossil pollen, and tree rings to reconstruct the environments in which plants, animals, and humans lived. By understanding ice ages, scientists can better predict how current and future climate changes might unfold, as the mechanisms that drove past ice ages, orbital variations, greenhouse gas fluctuations, and feedback loops still operate today. This knowledge highlights both the power of natural climate forces and the fragility of life in the face of major environmental shifts. The concepts of an ice age and a glacial period are often used interchangeably in everyday conversation, but in the realm of geology and earth science, they have distinct meanings that tell us very different stories about our planet's climate history. Understanding these differences requires us to look deeply at the Earth's past, millions of years of shifting climates, and the immense forces that drive these changes. Both ice ages and glacial periods describe times when the Earth experienced colder conditions than usual, but they differ in scale, duration, and effect on the planet. To explore this fully, we must begin by defining each term in precise yet accessible language, then examine how they relate, what causes them, and the remarkable evidence left behind that allows scientists to study them in such depth. An ice age is a prolonged period of time in Earth's history when the global climate is significantly colder than today, and large areas of the planet, particularly the continents at higher latitudes, are covered in ice sheets. Ice ages are not short-lived events. They extend over millions of years, spanning entire epochs, and involve a dramatic cooling of the planet's surface temperatures. During an ice age, glaciers, which are massive rivers of ice, expand far from their polar origins, covering vast portions of North America, Europe, and Asia. Today, Earth is actually still within a major ice age that began about 2,600,000 years ago, during the Pleistocene epoch. This ongoing ice age is often referred to as the Quaternary Ice Age, and it is characterized by alternating cycles of colder and warmer phases, showing that ice ages are not uniformly cold, but fluctuate over time. Within an ice age, there are shorter intervals known as glacial periods, sometimes also called glaciations. These are times when the ice sheets grow particularly large and temperatures drop to levels significantly colder than the surrounding climate periods. During glacial periods, ice can extend far into regions that are now temperate, such as the northern United States, much of northern Europe, and parts of Asia. These periods last tens of thousands to over 100,000 years, depending on the specific cycle. In between glacial periods, there are warmer intervals called interglacial periods, during which ice retreats toward the poles, sea levels rise, and the climate becomes more temperate. Currently, the Earth is in an interglacial period known as the Holocene, which began around 11,700 years ago, following the last major glacial period of the Pleistocene. To distinguish clearly, an ice age is the overarching era in which glacial periods occur. Think of an ice age as a long chapter in Earth's climate history book, spanning millions of years, while glacial periods are the individual sections of that chapter when the cold becomes particularly intense. For example, the Earth's most recent ice age, the Quaternary Ice Age, began approximately 2,600,000 years ago and continues to the present, though the ice has waxed and waned dramatically during that time. Within this ice age, multiple glacial periods occurred, each lasting tens of thousands of years, interspersed with warmer interglacial periods. The most recent glacial period, known as the last glacial maximum, reached its peak around 21,000 years ago, when ice sheets in North America, Northern Europe, and Northern Asia were at their maximum extent. The difference between an ice age and a glacial period can also be understood in terms of geography and ice coverage. During a full ice age, glaciers dominate large parts of the continents, but ice may not cover every landmass completely. The polar ice caps expand, mountain glaciers grow, and regions at higher latitudes experience prolonged cold conditions. Within this ice age, a glacial period represents a time when ice sheets extend to their farthest reaches, dramatically shaping the landscape by carving valleys, forming lakes, and depositing massive amounts of sediment. The advance and retreat of glaciers during glacial and interglacial periods leave behind features such as moraines, drumlins, and eskers, which are visible today in regions like the northern United States, Canada, Scandinavia, and Siberia. These landforms are direct evidence of glacial activity and allow scientists to reconstruct the scale and timing of glacial periods within a larger ice age. Causes of ice ages and glacial periods involve a complex interplay of factors, including Earth's orbit, axial tilt, solar radiation, atmospheric composition, and the arrangement of continents. One of the primary drivers of glacial cycles within an ice age is the variation in Earth's orbit and tilt, known as the Milankovitch cycles. These cycles include changes in eccentricity, or the shape of Earth's orbit around the Sun, which oscillates roughly every 100,000 years. Changes in axial tilt, which vary over 41,000 years, which oscillates roughly every 100,000 years. Changes in axial tilt, which vary over 41,000 years. And precession, or the wobble of Earth's axis, which cycles about every 23,000 years. These orbital changes alter the distribution of solar energy reaching Earth's surface, affecting the growth and retreat of glaciers. When summer temperatures in northern latitudes are cooler due to these orbital variations, snow and ice from winter may not fully melt, allowing glaciers to grow over successive years, ultimately leading to glacial periods. In addition to orbital changes, atmospheric levels of carbon dioxide and other greenhouse gases play a crucial role in controlling climate. Lower concentrations of carbon dioxide contribute to cooler global temperatures, while higher concentrations tend to warm the planet. During glacial periods, carbon dioxide levels were significantly lower than today, contributing to the growth of ice sheets. Other factors such as volcanic activity, ocean currents, and the position of continents also influence climate patterns and the onset of ice ages. For instance, the placement of large continents near the poles allows ice sheets to stabilize and expand, while open oceans can distribute heat more evenly, potentially delaying or limiting glaciation. The study of ice ages and glacial periods relies heavily on geological and paleoclimatic evidence. Scientists examine sediment cores from ocean floors, which contain layers of microscopic fossils, chemical signatures, and isotopic ratios that reflect past temperatures and ice volumes. Ice cores drilled from Greenland and Antarctica provide direct records of atmospheric composition, temperature, and even volcanic activity over hundreds of thousands of years. By analyzing these records, scientists can determine the timing, duration, and intensity of glacial periods within an ice age, as well as identify the interglacial periods when ice retreated. Fossil evidence, such as the distribution of plant and animal species, also provides clues about past climate conditions. During glacial periods, species adapted to cold climates expanded southward, while during interglacial periods, they retreated northward or moved to higher elevations. One of the most dramatic examples of glacial periods is the last glacial maximum, which occurred around 21,000 years ago. During this time, the Laurentide ice sheet covered most of Canada and extended into the northern United States, while the Fennoscandian ice sheet enveloped much of Scandinavia and northern Europe. Sea levels were approximately 120 meters lower than today, exposing vast areas of continental shelf and creating land bridges such as Beringia, which connected Asia and North America. These land bridges allowed humans and other animals to migrate across continents, profoundly influencing the distribution of species and human populations. The advance of glaciers during this period also reshaped river systems, formed glacial lakes, and left behind deposits that are still visible in landscapes today. Following the last glacial maximum, the Earth entered an interglacial period called the Holocene, beginning approximately 11,700 years ago. During this time, glaciers retreated to the polar regions, sea levels rose, and the climate became more stable and temperate. Human civilizations began to flourish during the Holocene, taking advantage of the warmer and more predictable climate for agriculture, settlement, and the development of cities. Despite the current warmth, the planet remains technically in an ice age because significant ice sheets still exist in Greenland and Antarctica, and the potential for future glacial periods remains as part of the ongoing Quaternary Ice Age cycle. Understanding the distinction between ice ages and glacial periods is crucial for comprehending the Earth's long-term climate patterns and the forces that shape our environment. An ice age represents a grand, extended period of cooler global conditions and polar ice expansion, lasting millions of years, whereas glacial periods are shorter, more intense episodes of ice growth within that ice age. The interplay of orbital mechanics, greenhouse gas levels, tectonic configurations, and oceanic circulation governs these cycles, producing the alternating advance and retreat of glaciers that have profoundly influenced the planet's landscapes and ecosystems. The study of these climatic phenomena also informs predictions about future climate behavior. By analyzing the patterns of past ice ages and glacial periods, scientists can model how factors like greenhouse gas emissions, solar activity, and changes in Earth's orbit may affect the timing and intensity of future glacial events. Although human activity is currently causing rapid global warming, which temporarily suppresses the advance of glaciers, the long-term natural cycles of ice ages and glacial periods are expected to continue, potentially affecting the Earth tens of thousands or even hundreds of thousands of years from now. In addition to their impact on climate and geography, ice ages and glacial periods have played a pivotal role in the evolution of life. The harsh conditions of glacial periods created selective pressures that shaped the adaptation of species. Organisms developed strategies to survive in cold, ice-dominated environments, including migration, hibernation, and specialized feeding habits. Interglacial periods, with their warmer climates, allowed species to expand into previously glaciated regions, promoting diversity and ecosystem complexity. These cycles of environmental change contributed to the evolution of many plant and animal lineages and influenced the distribution of species across continents. Ice ages also have a profound effect on human history and migration. The presence of ice sheets and lower sea levels during glacial periods opened land bridges that enabled humans to travel between continents. For example, the Bering Land Bridge allowed the first peoples to migrate from Siberia into the Americas approximately 25,000 years ago, during a glacial period when sea levels were significantly lower. Similarly, glacial and interglacial cycles influence the availability of resources, prompting humans to adapt their hunting, gathering, and agricultural practices to the changing environment. The knowledge of past ice ages helps anthropologists understand how early humans survived and spread across the globe. The differences between ice ages and glacial periods can be summarized in terms of time, scale, and impact. Ice ages are long-lasting, multi-million-year eras characterized by generally cold climates and the presence of large ice sheets at the poles. Within ice ages, glacial periods are shorter, tens of thousands of years in duration, when ice sheets grow to their maximum extent and reshape the Earth's surface. Interglacial periods within an ice age represent warmer intervals when ice retreats and climates stabilize. Together, these cycles of glacial advance and retreat create a rhythm in Earth's climate that has persisted for millions of years, leaving an indelible mark on the planet's geology, ecosystems, and human history. In essence, distinguishing an ice age from a glacial period allows us to understand the broader context of Earth's climate history and the specific intervals when glaciers dramatically advanced. Ice ages provide the long-term framework of cold climate conditions, while glacial periods mark the times of maximum glacial expansion within that framework. The study of these periods reveals the dynamic nature of Earth's climate, shaped by astronomical, atmospheric, and geological forces, and highlights the powerful role that ice has played in sculpting the landscapes we inhabit today. By examining sediment layers, ice cores, landforms, and fossil records, scientists piece together the history of ice ages and glacial periods, uncovering patterns that span millions of years. These investigations show that the Earth has experienced multiple major ice ages, including the Huronian Ice Age about 2,400,000,000 years ago, the Cryogenian Ice Age roughly 720 to 630 million years ago, the Andean-Saharan Ice Age around 450 to 420 million years ago, the Karoo Ice Age between 360 to 260 million years ago, and the current Quaternary Ice Age, which began about 2,600,000 years ago and continues to the present. Each of these ice ages contained multiple glacial periods, demonstrating that the pattern of glacial advance and retreat is a recurring feature of Earth's climate system. Through these repeated cycles, ice ages and glacial periods have profoundly influenced the development of landscapes, ecosystems, and human civilizations. Glacial erosion carved valleys, created lakes, and deposited soils that are crucial for agriculture today. The fluctuating climate forced plants, animals, and humans to adapt, migrate, or face extinction, shaping the evolutionary path of life on Earth. Modern climate scientists study these ancient patterns, not only to understand Earth's past, but also to anticipate future changes and to grasp the long-term consequences of ongoing human-induced warming. By recognizing the distinction between ice ages and glacial periods, we gain insight into the rhythm and dynamics of Earth's climate, the resilience of life, and the transformative power of ice in sculpting the planet. The earliest known ice ages took place more than 600 million years ago during the late Precambrian. During this time, Earth may have been almost entirely encased in ice, a period scientists sometimes call the snowball Earth phase. Evidence from glacial deposits in locations that are now near the equator suggests that ice sheets reached far beyond polar regions, covering much of the planet. The causes of this extreme cooling were likely a combination of low greenhouse gas levels, changes in the planet's orbit, and continental configurations that influenced how heat circulated across the Earth. This first known global-scale glaciation set the stage for the evolution of life by creating extreme challenges that only the most adaptable organisms could survive. Not long after the Precambrian, the Ordovician period brought another significant ice age around 440 million years ago. This cooling particularly affected the southern supercontinent of Gondwana, causing massive glaciers to expand and sea levels to fall as water became trapped in ice. Marine life suffered greatly during this period, with many species unable to survive the sudden climatic changes. The ice eventually melted around 435 million years ago, as volcanic activity released carbon dioxide into the atmosphere, warming the planet. These cycles of glaciation and deglaciation were beginning to establish a pattern that would continue throughout Earth's history. During the late Paleozoic era, roughly 350 to 280 million years ago, Earth experienced another prolonged ice age. This glaciation primarily affected Gondwana and persisted for tens of millions of years, with multiple periods of ice advance and retreat. During this time, extensive coal-forming forests grew in equatorial regions, demonstrating that even as ice dominated the southern continents, life continued to thrive elsewhere. The waxing and waning of these ice sheets caused sea levels to fluctuate dramatically, reshaping coastlines and influencing the evolution of plants and animals. The Mesozoic era, spanning from about 250 to 66 million years ago, is often remembered for its warm climates and the dominance of dinosaurs. But even during this period, the Earth was not immune to glacial episodes. Evidence suggests that some regions experienced cooler intervals, though not as extreme as the earlier ice ages. These periods of relative cold influenced ocean currents, wind patterns, and the distribution of vegetation, subtly affecting the ecosystems that were emerging across the planet. It was during the Cenozoic era, beginning about 66 million years ago, that ice ages became more pronounced in ways similar to what we think of today. Around 34 million years ago, the planet entered a period of significant cooling, leading to the formation of permanent ice sheets in Antarctica. This development marked a major shift in Earth's climate, as the planet transitioned from a generally warm state to one where large-scale glaciation could occur. Over the next tens of millions of years, these ice sheets grew, shrank, and reorganized, creating cycles of glaciation that would intensify in the late Pleistocene. The late Pleistocene, beginning roughly 2 million years ago, is the period most closely associated with ice ages in the human imagination. During this time, the Earth experienced repeated cycles of glacial and interglacial periods. Ice sheets advanced across North America, Europe, and Asia, sometimes reaching as far south as what is now the northern United States and Central Europe. These glaciers were immense, in some cases stretching over 3 miles thick, reshaping mountains, carving valleys, and grinding down rocks into soil that would later support new ecosystems. Between these glacial advances were interglacial periods, when the climate warmed, ice retreated, and forests, grasslands, and rivers flourished. One of the defining features of the late Pleistocene ice ages is their regularity, often following cycles of approximately 100,000 years. Scientists attribute these cycles to changes in Earth's orbit and tilt, known as Milankovitch cycles. These cycles affect the amount of solar energy reaching different parts of the planet, influencing when glaciers advance and retreat. During glacial periods, the global average temperature dropped by several degrees, sea levels fell by over 100 meters as water became locked in ice, and habitats shifted dramatically. These conditions shaped the evolution of many species, including early humans, who had to adapt to cold climates, scarce resources, and migrating herds of animals. The last major ice age, often called the last glacial maximum, reached its peak about 21,000 years ago. During this time, ice sheets were at their largest extent, covering much of Canada, northern Europe, and parts of Asia. The climate was extremely cold and dry, and large portions of the world that are now temperate or tropical were tundra or barren land. Humans survived this extreme period by developing new technologies, clothing, and strategies for hunting and gathering. As the ice began to melt around 12,000 years ago, sea levels rose, rivers carved new paths, and forests expanded into previously frozen areas, setting the stage for the rise of civilizations. Even today, the effects of ice ages are visible in the landscape. Glacial valleys, moraines, fjords, and other features bear witness to the slow, powerful movements of ice across continents. Lakes formed in depressions left by retreating glaciers, soil distributions reflect ancient glacial grinding, and sediments at the bottom of the oceans preserve records of temperature changes and ice growth over millions of years. Studying these features allows scientists to reconstruct past climates and understand the rhythms of ice ages, providing insight into how the Earth might respond to future changes in climate. Throughout Earth's long history, ice ages have not been continuous periods of cold, but rather cycles of advance and retreat, each with unique characteristics depending on the geography, atmospheric composition, and solar input at the time. Some ice ages lasted tens of millions of years, while others were shorter and more abrupt. Life has often been profoundly affected by these periods, with extinctions, migrations, and adaptations occurring as species responded to changing conditions. Plants, animals, and even early humans have been molded by these cycles, demonstrating the immense influence of ice ages on the evolution of life. The study of ice ages also provides crucial information for understanding climate change. By examining ice cores, sediments, fossils, and other geological records, scientists can see how carbon dioxide levels, temperatures, and ice sheet sizes changed in the past. This knowledge helps predict how modern climate systems might respond to increased greenhouse gases and other human-induced changes. In addition to their climatic and biological significance, ice ages have played a critical role in shaping human history. The retreat of the last ice sheets created the landscapes on which agriculture, settlements, and civilizations developed. Fertile soils formed in glacial deposits allowed crops to grow. Rivers reshaped by melting ice provided transportation and water sources, and natural barriers like mountains and glaciers influenced migration and the spread of cultures. The echoes of ice ages can be traced in human societies, not only in physical geography, but also in mythology, folklore, and cultural memory, where ancient peoples often recounted stories of great floods, cold winters, and strange frozen lands. The last 100,000-year Ice Age cycle is one of the most striking examples of how slowly and powerfully Earth's climate can change. Over this long stretch of time, the planet has experienced immense swings in temperature, ice coverage, and sea levels, shaping the landscapes, ecosystems, and even the evolution of humanity. These cycles, known as glacial interglacial cycles, are governed by precise rhythms in Earth's movement through space, combined with feedback effects in the atmosphere, oceans, and ice sheets that amplify the cold and warmth over tens of thousands of years. Understanding this cycle requires examining the gradual buildup of ice, the shifting climate patterns, and the dramatic transformations of the environment over spans far longer than human history. During a typical glacial period within this last 100,000-year cycle, ice sheets expanded to cover enormous portions of the northern hemisphere. North America, Northern Europe, and parts of Asia were largely beneath thick layers of ice, some reaching up to several kilometers in depth. The growing ice sheets reshaped the land, carving deep valleys, forming massive lakes, and flattening mountains. The advancing ice also caused sea levels to drop by over 120 meters, exposing land bridges that connected continents, allowing humans and animals to migrate to new areas that would otherwise have been unreachable. The climate in these periods was harsh and dry in many regions, with winds sweeping across the frozen landscapes and deserts expanding in areas that are now temperate. Interglacial periods, by contrast, were times when the ice sheets melted back toward the poles, oceans rose, and the climate warmed enough to allow forests, grasslands, and wetlands to flourish across lands that had been frozen or barren. The most recent interglacial, which began roughly 11,700 years ago, allowed human civilizations to develop agriculture, settle in permanent villages, and build the first cities. Each glacial interglacial cycle included not just a cold phase and a warm phase, but also gradual transitions in between, where temperatures and ice coverage slowly shifted over thousands of years, giving ecosystems and species time to adapt, migrate, or face extinction. One of the main forces behind these cycles is the natural variation in Earth's orbit and tilt, known collectively as Milankovitch cycles. There are three key types of variations: changes in the eccentricity of Earth's orbit, which alter the shape of the orbit from nearly circular to more oval-shaped over roughly 100,000 years; changes in the tilt of Earth's axis, which vary between about 22 and 24.5 degrees over approximately 41,000 years; and the wobble of Earth's axis, called precession, which shifts the timing of seasons over cycles of roughly 26,000 years. These orbital shifts change the amount and distribution of solar energy reaching Earth, influencing when ice sheets grow and melt. The interplay of these cycles means that the timing of glacial advances and retreats is highly predictable on geological timescales, even if the exact climate conditions fluctuate locally. However, orbital changes alone cannot explain the full magnitude of ice age cycles. Feedback processes in the climate system amplify the initial effects of orbital variations. For example, as ice sheets grow, their reflective surfaces increase the amount of sunlight bounced back into space, cooling the planet further and encouraging more ice growth. Similarly, as ice melts during interglacial periods, darker land and ocean surfaces absorb more sunlight, reinforcing warming and accelerating the retreat of ice. Atmospheric carbon dioxide also plays a crucial role. During glacial periods, carbon dioxide levels dropped significantly, reducing greenhouse warming, while during interglacial periods, CO2 levels rose, trapping more heat in the atmosphere. Ocean currents further influenced ice ages by redistributing heat around the planet, bringing warmth to some regions while reinforcing cold in others. Evidence for the last 100,000-year ice age cycle comes from many sources, including deep-sea sediment cores, ice cores from Greenland and Antarctica, fossil records, and geological formations. Ice cores, in particular, provide detailed records of past temperatures, atmospheric composition, and volcanic activity. Tiny bubbles of ancient air trapped in ice reveal carbon dioxide and methane levels from hundreds of thousands of years ago, allowing scientists to reconstruct how greenhouse gases fluctuated along with the ice sheets. Sediment cores from the ocean floor contain layers of particles that were carried from continents by wind and rivers, offering clues about past glacial advances and retreats. Fossils of plants and animals also show how ecosystems shifted as the ice waxed and waned, with species migrating, adapting, or dying out in response to changing climate conditions. The last 100,000-year cycle includes several distinct glacial and interglacial phases. Roughly 120,000 years ago, the planet was in a warm interglacial period known as the Eemian, when ice sheets were smaller than during the later last glacial maximum, and sea levels were higher than today by as much as 6 to 9 meters. Temperatures were also warmer than the pre-industrial world, allowing forests to spread across northern Europe and supporting diverse wildlife. Following the Eemian, ice sheets began their long advance toward the last glacial maximum, which peaked around 21,000 years ago. During this time, ice sheets reached their maximum extent, covering much of Canada, the northern United States, northern Europe, and Siberia. Sea levels dropped dramatically, exposing land bridges such as Beringia between Asia and North America, which allowed humans and animals to migrate across continents. The end of this last ice age cycle was marked by gradual warming, beginning around 19,000 years ago and accelerating after 16,000 years ago. The melting of ice sheets raised sea levels and reshaped coastlines worldwide. Lakes and rivers expanded, forests replaced tundra in many regions, and ecosystems became more complex. This period of deglaciation coincided with the rise of human civilization as Homo sapiens adapted to new environments, developed agriculture, and established permanent settlements. In regions like the Fertile Crescent, the retreat of glaciers and the expansion of fertile soils created the conditions for the first farming communities, which eventually led to cities, writing, and organized societies. The climate shifts during this cycle were not smooth or uniform. Within the glacial periods, there were shorter warming events, known as interstadials, where temperatures temporarily rose and ice sheets partially retreated, followed by renewed cold. Similarly, within interglacial periods, brief cooling events occurred. These fluctuations show that climate is a complex system influenced by multiple factors, including volcanic eruptions, ocean circulation changes, solar activity, and atmospheric composition. For example, large volcanic eruptions could inject dust and aerosols into the atmosphere, temporarily cooling the planet, while shifts in ocean currents could redistribute heat in ways that intensified or moderated regional climates. The 100,000-year cycle of ice ages also illustrates how life on Earth responds to long-term climate changes. Many species evolved strategies to survive the cold, such as hibernation, migration, and changes in body size or behavior. Forests and grasslands shifted their boundaries, creating new habitats and corridors for animals. Humans adapted by developing tools, clothing, and shelters to survive in harsh glacial environments, while taking advantage of resources exposed by retreating ice sheets during warmer phases. These adaptations highlight the deep interconnection between climate and life, showing that the rhythm of ice and warmth shapes ecosystems, species evolution, and human history alike. In addition, the cycle had profound effects on the geography of the continents. As ice sheets advanced, they sculpted mountains, carved valleys, and created glacial lakes. Retreating glaciers left behind moraines, outwash plains, and fjords, many of which still define the landscapes of North America, Europe, and Asia. Sea level changes exposed and submerged coastal areas, affecting the distribution of marine and terrestrial habitats. Some islands were temporarily connected to continents, while shallow seas retreated, altering ocean currents and influencing global climate patterns. The physical imprint of this cycle remains visible today. Earth's climate history is meticulously preserved in the frozen layers of ice that blanket Greenland, Antarctica, and other polar regions. These ice sheets, which can reach several kilometers in thickness, hold an extraordinary archive of the atmosphere, snowfall, and environmental conditions spanning hundreds of thousands of years. Within these layers are tiny bubbles of air, trapped at the exact moment each snowfall occurred. These bubbles contain the same gases that existed in the atmosphere long ago, such as carbon dioxide and methane, providing a direct window into the planet's climate of the past. Dust, volcanic ash, and other microscopic particles are also preserved, offering clues about natural events, like massive volcanic eruptions, wind patterns, and even desert activity, at specific moments in time. Ice cores are obtained by drilling long cylinders of ice from the thickest parts of ice sheets. The deepest cores, such as those from central Antarctica, can reach lengths of more than 3 kilometers, representing continuous records going back over 800,000 years. In Greenland, cores have revealed detailed climate records stretching back over 120,000 years. Each centimeter of ice corresponds to months, seasons, or years of snowfall, and the layers build up in sequence, allowing scientists to create precise timelines of past climate changes. By analyzing the composition of the ice and the gases trapped within, scientists can determine past temperatures, concentrations of greenhouse gases, and major climate events, including ice ages and interglacial periods. One of the most important features of ice cores is the ratio of oxygen isotopes in the water molecules. Water molecules contain oxygen atoms that come in slightly different forms, called isotopes. The ratio of heavier oxygen isotopes to lighter ones changes depending on temperature. When temperatures are warmer, more of the heavier isotopes evaporate from the oceans and fall as precipitation, while colder temperatures favor lighter isotopes. By measuring these ratios in different layers of ice, scientists can reconstruct detailed temperature records going back hundreds of thousands of years. This method has revealed the cyclical nature of Earth's climate, showing alternating periods of cold, glacial conditions and warmer, interglacial periods. These cycles often occur on scales of tens of thousands to hundreds of thousands of years, closely linked to subtle changes in Earth's orbit and tilt, which affect the amount of sunlight reaching different parts of the planet. The air bubbles trapped within ice cores provide an equally valuable record of greenhouse gases. Measurements of carbon dioxide, methane, and nitrous oxide in these bubbles show that during glacial periods, greenhouse gas concentrations were much lower than during warmer interglacial periods. For example, carbon dioxide levels were around 180 to 200 parts per million during the last ice age, which ended about 11,700 years ago, compared to over 400 parts per million in the present day. Methane, another potent greenhouse gas, also followed similar patterns, with concentrations rising during warmer periods and falling during colder ones. This evidence confirms the strong connection between greenhouse gases and global temperatures, demonstrating that small changes in atmospheric composition can have large effects on Earth's climate. Ice cores also capture evidence of sudden and dramatic climate events. Layers of volcanic ash, known as tephra, indicate massive volcanic eruptions that injected dust and aerosols into the atmosphere, temporarily cooling the planet. For instance, ash layers corresponding to the eruption of Mount Toba in Indonesia, which occurred about 74,000 years ago, are found in ice cores thousands of kilometers away, showing how powerful eruptions can impact global climate. Similarly, sudden spikes in dust concentrations indicate periods of extreme aridity or large-scale windstorms, reflecting changes in vegetation and soil cover. These abrupt events often coincide with rapid shifts in temperature and greenhouse gas concentrations, showing that Earth's climate can change surprisingly quickly under certain conditions. Greenland ice cores provide particularly detailed insights into the climate of the Northern Hemisphere during the last glacial period. These cores reveal abrupt warming events known as Dansgaard-Oeschger events, where temperatures in Greenland rose by as much as 8 to 10 degrees Celsius within decades. Such rapid warming demonstrates the climate system's sensitivity and the potential for sudden changes. In Antarctica, ice cores reveal slightly different patterns, with temperature changes generally occurring more gradually, highlighting regional differences in climate response. By comparing cores from both poles, scientists can study how climate shifts propagate across the planet and how the northern and southern hemispheres interact over time. Another critical contribution of ice cores is the ability to study past sea levels indirectly. Ice sheet volume and extent are closely linked to global sea levels. During glacial periods, when ice sheets expanded, sea levels dropped significantly, sometimes by over 120 meters compared to today. By examining the isotopic composition of ice and the trapped air, scientists can infer changes in ice volume and consequently reconstruct past sea level variations. This information is vital for understanding how the climate system responds to temperature changes and for predicting future sea level rise in a warming world. Ice cores also record evidence of human impacts on the climate in recent centuries. Layers deposited during the industrial era show increased concentrations of carbon dioxide and methane, as well as pollutants such as lead and black carbon from burning fossil fuels. These records provide a direct comparison between natural climate variability over thousands of years and human-induced changes occurring over just a few centuries. The analysis of ice cores relies on a combination of chemical, isotopic, and physical techniques. Scientists measure the concentration of gases, isotopic ratios, and trace elements in each layer, often using highly sensitive instruments that can detect parts per billion. They also study the crystal structure of ice, which can reveal past temperatures and stress conditions within the ice sheet. In addition, layers of dust and pollen trapped in the ice provide information about past vegetation, wind patterns, and desertification. Together, these multiple lines of evidence allow researchers to reconstruct a remarkably detailed and nuanced picture of Earth's climate history. Ice cores have been central to understanding the timing and causes of glacial and interglacial cycles. These cycles, which dominate the last 100,000 years of Earth's climate history, are driven by variations in Earth's orbit, axial tilt, and wobble, collectively known as Milankovitch cycles. Ice core data show that changes in solar radiation associated with these orbital variations correspond closely with the advance and retreat of ice sheets. However, the cores also reveal that orbital changes alone cannot explain the full amplitude of climate swings. Feedbacks involving greenhouse gases, ice albedo, and ocean circulation amplify the effects, producing the dramatic temperature differences observed between glacial and interglacial periods. The oldest ice cores provide a record of even more ancient climate events. In Antarctica, cores from the Dome C and Dome Fuji regions extend back over 800,000 years, capturing 8 complete glacial cycles. These records show that the last ice age cycle, which ended around 11,700 years ago, was part of a long series of ice ages occurring roughly every 100,000 years. Interestingly, the cores also reveal that earlier cycles, such as those occurring around 400,000 years ago, had slightly shorter durations of roughly 40,000 years, suggesting that the climate system's response to orbital forcing has changed over time. This insight helps scientists understand the natural variability of the Earth system and provides context for current climate change. Ice cores do not only tell the story of the past, they also inform predictions about the future. By understanding how temperatures, greenhouse gases, and ice sheets have interacted over hundreds of thousands of years, scientists can better anticipate how the climate will respond to ongoing human activities. Models of future climate rely heavily on the data preserved in ice cores, which provide benchmarks for natural variability and the sensitivity of the climate system. In this way, ice cores act not just as historical records, but as guides for making informed decisions about mitigation and adaptation in the present. The detailed analysis of ice cores has revealed the interconnectedness of various components of the climate system. For example, changes in ocean circulation, such as the slowing or acceleration of the Atlantic meridional overturning circulation, are reflected in isotopic variations in the ice. Similarly, the timing of monsoons, recorded in dust and isotopic compositions, is linked to temperature changes and ice volume. These connections show that Earth's climate is a complex web of interacting systems, where a change in one part of the globe can have cascading effects across continents and oceans. Ice cores, with their finely layered structure and preserved chemical signals, are one of the few archives capable of capturing this complexity with such clarity. The scientific study of ice cores has expanded rapidly since the mid-20th century. Early drilling projects in Greenland and Antarctica were small-scale and focused on short-term climate records, but advances in technology have enabled researchers to drill deeper and extract longer, more complete cores. Modern ice core projects often involve international collaboration, with teams from multiple countries working together to retrieve, transport, and analyze cores from some of the most remote and inhospitable regions on Earth. These projects not only advance our understanding of climate history, but also foster cooperation and knowledge sharing among scientists worldwide. In addition to providing quantitative data, ice cores offer a qualitative sense of Earth's environmental history. Layers of ice often contain visible ash from volcanic eruptions, layers of wind-blown dust, and even trapped microorganisms, giving a tangible sense of the conditions at the time the ice formed. By examining the physical appearance and structure of the ice, scientists can infer seasonal patterns, storm events, and even past snowfall amounts. This combination of chemical, isotopic, and visual information creates a rich, multidimensional record that can be read much like a detailed historical manuscript. Ice cores have transformed our understanding of the natural rhythms of Earth's climate. They have revealed the timing, magnitude, and speed of past climate changes, the role of greenhouse gases in amplifying these changes, and the interplay between ice sheets, oceans, and the atmosphere. They have documented abrupt climate events, volcanic eruptions, and long-term trends, offering a continuous record that spans hundreds of thousands of years. Perhaps most importantly, ice cores provide a context for understanding the rapid changes currently occurring due to human activity. Ice sheets are among the most remarkable features of our planet. Vast expanses of ice that can stretch across entire continents and reach thicknesses of several kilometers. Their growth and melting are not simple processes. They are the results of intricate interactions between climate, geography, and the ice itself. Central to these interactions are feedback mechanisms, processes that can either amplify changes or counteract them, shaping the behavior of ice sheets over thousands of years. These feedbacks make ice sheets highly sensitive to small shifts in temperature, precipitation, or ocean currents, yet their responses often unfold slowly, on timescales that span decades, centuries, or even tens of thousands of years. Understanding these mechanisms is crucial because ice sheets influence global sea levels, ocean circulation, and even the climate of regions far from the ice itself. One of the most fundamental feedback mechanisms is the relationship between ice and sunlight. Ice is highly reflective. It bounces most of the sunlight that hits it back into the atmosphere. This property, known as albedo, acts as a natural brake on warming. When ice sheets grow, their increasing surface area reflects more sunlight, which helps keep the surrounding environment colder and allows even more ice to accumulate. Conversely, When ice melts and exposes darker land or ocean beneath, more sunlight is absorbed, which accelerates warming and leads to further melting. This positive feedback, where a change in one direction amplifies itself, can turn small climatic shifts into major transformations in the size of ice sheets. Temperature changes also interact with ice sheets through a more direct physical feedback. Ice flows slowly under its own weight, and its movement is influenced by both surface temperature and the presence of liquid water at its base. Warmer temperatures can melt the ice from above, creating meltwater that percolates through cracks and crevasses, lubricating the base and allowing the ice to slide more rapidly. This faster flow can lead to more ice being discharged into the ocean, raising sea levels and exposing the edges of the ice sheet to warmer waters, which accelerates melting. In this way, temperature-driven melting can feed itself through both surface and basal processes. Precipitation patterns form another layer of complexity in ice sheet feedbacks. Ice sheets gain mass primarily through snowfall, and the amount of snowfall is influenced by the climate, which in turn is affected by the presence of the ice itself. Large ice sheets can alter atmospheric circulation, creating colder and drier conditions in some regions while increasing precipitation in others. If snowfall increases, the ice sheet gains mass and can expand further, reflecting more sunlight and reinforcing colder conditions locally. However, if warming reduces snowfall or increases rain, the accumulation slows, weakening the ice sheet and making it more vulnerable to melting. This interplay between climate, precipitation, and ice growth demonstrates how feedbacks can either stabilize or destabilize ice sheets depending on broader environmental conditions. Ocean interactions provide yet another crucial feedback mechanism. Ice sheets that extend to the sea can lose mass through the calving of icebergs, a process in which chunks of ice break off and float away. The rate of calving is strongly influenced by ocean temperatures. Warmer waters erode the ice from below, thinning the ice shelves that hold back inland ice. As these shelves weaken or collapse, the inland ice accelerates toward the sea, further increasing ice loss. This connection between ice and ocean is a clear example of a positive feedback. Melting at the edges triggers further melting inland, creating a self-reinforcing cycle. Conversely, colder ocean currents can slow melting and provide a stabilizing influence, showing how feedbacks can operate in both directions. Ice sheets also interact with the land beneath them, creating what is known as bedrock feedbacks. The immense weight of ice depresses the Earth's crust, a process called isostatic depression. As ice melts, the land slowly rises back toward its original position, altering local slopes and drainage patterns. This uplift can influence how water flows beneath the ice, changing the dynamics of melting and flow. For example, rising land can reduce the gradient that drives ice toward the ocean, slowing discharge and stabilizing the ice sheet. However, in some configurations, uplift can redirect meltwater to areas where it enhances basal lubrication, accelerating ice movement. These land-ice interactions add another layer of complexity to feedbacks, linking ice dynamics to geological processes over thousands of years. Internal ice dynamics themselves provide additional feedbacks. Ice is not static, it deforms, fractures, and flows in response to stress. Crevasses, meltwater channels, and subglacial lakes all influence how ice moves. Meltwater can enter cracks, penetrate to the base, and create pathways that increase flow speed. Subglacial lakes can act as lubricants, allowing ice to slide more efficiently. At the same time, the ice itself can redistribute mass, thickening in some areas and thinning in others, which affects pressure, flow direction, and stability. These internal processes are self-regulating in some cases and self-amplifying in others, demonstrating the subtle interplay of feedbacks within the ice sheet. The climate system outside the ice sheet is equally influential. Changes in atmospheric carbon dioxide and other greenhouse gases alter global temperatures, directly impacting ice sheet growth and melting. When greenhouse gas concentrations rise, temperatures increase, accelerating surface melting and ocean warming, which in turn destabilizes ice sheets. This interaction creates a feedback loop linking human activity to ice sheet dynamics, as modern industrial emissions have begun to influence these natural processes on timescales of decades, which is much faster than the natural cycles that have controlled ice sheets for millennia. Feedbacks also operate on larger planetary scales through their influence on sea level. As ice sheets lose mass, global sea levels rise, which can lead to further melting at the margins of remaining ice sheets. Rising seas can intrude into fjords and valleys where ice flows to the ocean, increasing calving rates and promoting additional loss. On the other hand, when ice sheets grow and lock up more water as ice, sea levels fall, which can create more land exposure, alter ocean currents, and change regional climates in ways that can either promote or inhibit further ice growth. These global-scale feedbacks connect distant parts of the Earth, linking polar ice sheets to tropical and temperate regions far from the ice itself. Historical evidence from past ice ages shows how feedback mechanisms have shaped the rise and fall of ice sheets. During the last glacial maximum, roughly 20,000 years ago, ice sheets covered large parts of North America, Northern Europe, and Asia. Their growth was fueled by colder global temperatures, increased snowfall, and high reflectivity that reinforced cooling. When warming began around 18,000 years ago, melting accelerated, driven by rising temperatures, ocean warming, and the albedo effect as ice retreated and exposed darker surfaces. These feedbacks combined to drive rapid changes in ice sheet size over a few thousand years, demonstrating the power of interconnected processes in controlling the Earth's frozen regions. Even subtle shifts in orbital patterns influence ice sheet feedbacks. Changes in the Earth's tilt, orbit shape, and wobble affect the distribution of sunlight across the planet, altering the timing and intensity of seasons. These variations influence snow accumulation and summer melting, which in turn interact with all the feedbacks described above. Over tens of thousands of years, these astronomical cycles have repeatedly triggered the growth and decay of ice sheets, illustrating how feedback mechanisms translate small external changes into major transformations in the Earth's surface. The interaction between ice sheets and ecosystems also adds an ecological dimension to feedbacks. As ice advances, it reshapes landscapes, altering river courses, soil development, and vegetation patterns. When ice retreats, newly exposed land is colonized by plants and animals, which can influence local albedo, moisture retention, and carbon storage. These biological processes feed back into climate and ice sheet dynamics in subtle ways. For instance, vegetation growth on newly exposed land can reduce albedo slightly, absorbing more sunlight and promoting local warming, which may contribute to further ice melt. Conversely, the growth of reflective surfaces such as snow-covered tundra can slow regional warming, stabilizing remaining ice. Human activities are now interacting with these natural feedbacks in unprecedented ways. Industrial emissions, deforestation, and land use changes are altering the atmospheric composition, warming oceans, and shifting precipitation patterns. These changes accelerate melting at the edges of Greenland and Antarctic ice sheets, triggering feedbacks that amplify ice loss. Sea level rise from this melting threatens coastal communities and alters ocean circulation patterns, which may feed back to further destabilize ice sheets. In this sense, feedback mechanisms are no longer purely natural. Human influence has become an integral part of the system, highlighting the urgency of understanding how ice sheets respond to changing conditions. Ice sheet feedbacks are not uniform across all regions. The Greenland ice sheet behaves differently from the Antarctic ice sheet because of differences in geography, climate, and ocean interactions. Greenland is more exposed to warm air and ocean currents, making its edges particularly sensitive to melting. Antarctic ice sheets are more isolated and influenced by cold ocean currents and thick ice shelves, which can temporarily buffer melting but are vulnerable to collapse if the surrounding waters warm. Understanding these regional differences is critical for predicting future changes and their global consequences. The interplay of all these feedbacks, albedo effects, temperature-driven melting, precipitation patterns, ocean interactions, bedrock response, internal ice dynamics, atmospheric composition, orbital variations, ecological factors, and human activity, makes ice sheets dynamic, complex systems. They are simultaneously fragile and resilient, capable of enormous growth under favorable conditions, but also vulnerable to rapid loss when multiple feedbacks act in concert. This delicate balance explains why ice sheets can persist for tens of thousands of years, but can also change dramatically within just a few centuries or even decades. Modern observations provide real-time evidence of these processes. Satellite measurements reveal thinning ice shelves, accelerating glaciers, and the formation of meltwater lakes that feed basal lubrication. Ocean probes show warming waters under floating ice shelves, while airborne surveys detect subtle changes in ice elevation and movement. These observations confirm that feedback mechanisms are actively shaping ice sheets today, responding to both natural variability and human-driven changes. By studying these processes carefully, scientists can better predict how ice sheets will behave in the coming centuries, how sea levels will change, and what implications these changes will have for global climate and human societies. The Milankovitch cycles are one of the most fascinating and important ways we can understand the timing of ice ages on Earth. These cycles are named after a Serbian mathematician and engineer, Milutin Milankovitch, who spent much of his life studying how subtle changes in Earth's movement could influence the climate over thousands and even hundreds of thousands of years. His work has become a cornerstone of paleoclimatology, the study of Earth's ancient climates, because it provides a mechanism for why the planet alternates between long, cold glacial periods and shorter, warmer interglacial periods. These cycles are driven by predictable variations in Earth's orbit and tilt, which change the way sunlight falls on the planet and, over time, can trigger profound changes in the climate. There are three main types of Milankovitch cycles: eccentricity, obliquity, and precession. Each affects the Earth's climate in a different way, and together they create a complex rhythm that helps explain the pacing of ice ages. The first type, eccentricity, refers to changes in the shape of Earth's orbit around the Sun. Earth does not travel in a perfect circle. Instead, its orbit is slightly elliptical. Over periods of roughly 100,000 years, the orbit shifts from being more circular to more oval-shaped and back again. When the orbit is more elliptical, the distance between Earth and the Sun changes more dramatically over the course of a year. This change alters the amount of solar energy that reaches the planet, especially during the critical summer months in the northern hemisphere, where most ice sheets grow and melt. Small differences in the intensity of sunlight during summer can determine whether snow survives the warmer season or melts completely. If snow survives, it gradually builds up into ice sheets, triggering the start of a glacial period. When summers become warmer and snow melts more completely, ice sheets shrink and the climate enters an interglacial period. The second type, obliquity, refers to changes in the tilt of Earth's axis relative to its orbital plane. Today, Earth's axis is tilted at an angle of about 23 degrees and 26 minutes, but over a cycle of roughly 41,000 years, this tilt varies between about 22 and 24.5 degrees. A greater tilt causes more extreme seasons, making summers hotter and winters colder. A smaller tilt reduces seasonal extremes, resulting in cooler summers and milder winters. These shifts in tilt strongly influence ice sheet growth, because cooler summers allow snow to persist and accumulate into massive ice sheets. Conversely, hotter summers tend to melt existing ice more rapidly, reducing the extent of glacial coverage. This cycle of tilt variation thus contributes to the waxing and waning of ice ages, complementing the orbital eccentricity cycle. The third type, precession, is the wobble of Earth's axis, much like the slow spinning of a top. Precession affects the timing of seasons in relation to Earth's orbit around the Sun. This wobble occurs over a cycle of approximately 26,000 years. It means that the northern and southern hemispheres alternately experience summer when Earth is closer to the Sun and winter when it is farther away. This shift changes the intensity of seasons in each hemisphere, altering the growth and melting patterns of ice sheets. When northern summers occur at the farthest point from the Sun, they are cooler, favoring ice accumulation, while southern summers become warmer. Over thousands of years, these subtle changes in sunlight distribution can combine with eccentricity and obliquity to amplify or dampen glacial cycles. The interaction of these three cycles is complex, and it is this interplay that produces the rhythm of ice ages. While each cycle has its own period, they do not operate in isolation. Instead, they reinforce or counteract each other in ways that can either accelerate the onset of glacial periods or prolong warm interglacials. For example, if eccentricity, obliquity, and precession all align in a way that makes northern hemisphere summers cooler, ice sheets are more likely to expand rapidly, creating a new glacial period. Conversely, if the cycles combine to produce unusually warm summers, ice sheets retreat and an interglacial period emerges. The timing of these cycles explains why ice ages do not occur at perfectly regular intervals, but rather fluctuate over tens of thousands of years, with the last glacial maximum peaking approximately 21,000 years ago. Evidence for the influence of Milankovitch cycles comes from multiple sources, including the study of deep ocean sediments, fossils, and particularly ice cores. Ice cores drilled from Greenland and Antarctica preserve layers of ice that accumulated year after year over hundreds of thousands of years. These layers trap tiny air bubbles, which contain samples of ancient atmospheres, including greenhouse gases like carbon dioxide and methane. By analyzing the chemical composition of these trapped gases, scientists can reconstruct past temperatures and atmospheric conditions with remarkable precision. The layers also capture dust, volcanic ash, and other particles that provide further clues about historical climate events. When these records are compared with the timing predicted by Milankovitch cycles, a strong correlation emerges, showing that Earth's orbital variations have indeed paced the advance and retreat of ice sheets for hundreds of thousands of years. One of the most striking examples of this connection is the pattern of ice ages over the past 1 million years. Studies of sediment cores from the ocean floor reveal cycles of glacial and interglacial periods occurring roughly every 100,000 years, closely matching the period of orbital eccentricity. Within these broader cycles, shorter fluctuations of 41,000 years and 26,000 years, corresponding to obliquity and precession, are also evident. These findings confirm that Milankovitch cycles are not just theoretical concepts, but are actually recorded in the geological history of the planet. They provide a natural clock that can be used to understand past climate changes and predict potential future trends. Milankovitch cycles also help explain why ice ages tend to be asymmetric. Glacial periods are generally long, lasting tens of thousands of years, while interglacials are relatively short, often only a few thousand years. This asymmetry arises from the way solar radiation interacts with ice sheets and the oceans. During periods when summer insolation in the northern hemisphere is low, ice sheets gradually grow, reflecting more sunlight and cooling the planet further. This positive feedback slows the melting process and prolongs glacial periods. Conversely, when summer insolation is high, ice sheets melt relatively quickly, ending the glacial period and creating a brief, warm interglacial. The combination of orbital mechanics, solar energy, and feedback mechanisms in Earth's climate system explains why ice ages follow this distinctive pattern. The impact of Milankovitch cycles extends beyond the timing of ice ages. They influence sea levels, ocean circulation, and even the evolution of life. During glacial periods, vast amounts of water are locked up in ice sheets, causing global sea levels to drop by more than 120 meters in some cases. This exposes continental shelves and alters coastlines, creating land bridges that allow species to migrate between continents. Conversely, during interglacials, melting ice sheets raise sea levels, submerging these land bridges and isolating populations. These shifts can drive evolution, speciation, and migration patterns, shaping the diversity of life on Earth over geological timescales. The cycles also affect atmospheric composition and ocean chemistry. As ice sheets grow, the carbon cycle is influenced by changes in vegetation, soil carbon, and the exchange of carbon dioxide between the oceans and the atmosphere. Cooler oceans can absorb more carbon dioxide, further lowering greenhouse gas concentrations and reinforcing glacial conditions. During interglacial periods, warmer oceans release carbon dioxide, amplifying warming trends. Milankovitch cycles, therefore, are not only mechanical drivers of sunlight distribution, but also catalysts for complex chemical and biological feedbacks that control Earth's climate system. Human history and prehistory have also been shaped indirectly by Milankovitch cycles. Early humans evolved during a time of repeated glacial and interglacial fluctuations, which altered habitats, food availability, and migration routes. The spread of Homo sapiens out of Africa and into Eurasia, for instance, coincided with periods of relatively mild climate that allowed the expansion into new territories. The cycles influenced the growth of forests, savannas, and grasslands, which in turn affected the animals that early humans hunted and the plants they gathered. Even agriculture, which emerged only about 12,000 years ago, was enabled by the relatively stable interglacial conditions that followed the last glacial maximum. Modern climate scientists continue to study Milankovitch cycles not only to understand the past, but also to predict the future. While current global warming is largely driven by human activities, such as the burning of fossil fuels and deforestation, the underlying rhythm of orbital cycles still plays a role in modulating natural climate variability. Understanding these cycles helps scientists separate human-induced changes from natural patterns and improves climate models that forecast long-term trends. Moreover, the study of Milankovitch cycles provides a humbling perspective on the immense timescales over which the Earth's climate operates. It is important to note that while Milankovitch cycles are powerful drivers of climate change, they do not act alone. The Earth system is complex, and feedback mechanisms involving the atmosphere, oceans, ice sheets, and biosphere amplify or dampen the effects of orbital changes. Volcanic eruptions, tectonic activity, and variations in solar output can all influence climate on shorter timescales. Nevertheless, Milankovitch cycles set the stage for the grand pacing of ice ages, providing a predictable framework within which other factors operate. Their discovery was a monumental leap in our understanding of Earth's climate, bridging the gap between celestial mechanics and terrestrial geology. The recognition of Milankovitch cycles also illustrates the remarkable foresight and diligence of Milutin Milankovitch. In the early decades of the 20th century, he meticulously calculated how changes in Earth's orbit, tilt, and wobble would alter the distribution of sunlight across the globe. At a time when technology was limited and computer modeling was non-existent, he used mathematical tables and painstaking calculations to predict climate patterns that would only be confirmed decades later through ice core and sediment data. His work demonstrates the power of careful observation, mathematics, and imagination in unraveling the complex workings of our planet. The cumulative effect of these cycles over millions of years can be seen in the extensive ice sheets that once covered North America, Europe, and Asia. These sheets, sometimes several kilometers thick, sculpted the land, carved valleys, and left behind vast deposits of sediment. They created the lakes, rivers, and fertile plains that modern civilizations depend upon. The rise and fall of ice ages, driven by Milankovitch cycles, thus shaped not only the climate, but also the very geography of continents, influencing human settlement patterns and the distribution of natural resources. Furthermore, Milankovitch cycles demonstrate the extraordinary sensitivity of Earth's climate system. Even small changes in solar radiation, amounting to a fraction of a percent, can trigger massive environmental transformations when amplified by feedback mechanisms involving ice, oceans, and the atmosphere. This sensitivity explains why ice ages can occur despite the relative stability of the sun's energy output, and why understanding the intricate interplay of orbital mechanics and climate feedbacks is essential for comprehending both past and future climate change. Modern research continues to refine our understanding of Milankovitch cycles. Advanced satellite observations, high-precision ice core measurements, and sophisticated climate models allow scientists to explore the exact timing and magnitude of past glacial cycles. These studies reveal that while the cycles themselves are predictable, their effects on climate are modulated by factors such as greenhouse gas concentrations, ocean currents, and continental positions. Such research underscores the interconnectedness of Earth's climate system and highlights the ongoing relevance of Milankovitch's early 20th century insights. The legacy of Milankovitch cycles extends beyond pure science. They inspire awe at the delicate balance that sustains Earth's climate, showing how forces operating on timescales far beyond a human lifetime can govern the rhythms of ice and warmth, shaping the destiny of landscapes and species over hundreds of thousands of years. The evidence is everywhere in the ice cores of Greenland and Antarctica, in the layers of ocean sediments, and in the fossil record of the continents. Each layer, each fossil, each measurement of past greenhouse gases confirms the rhythm first predicted by Milankovitch almost a century ago. The cycles provide a window into the deep past, allowing scientists to trace the march of ice ages over millions of years, to see the rise and retreat of ice sheets, and to understand the environmental pressures that shaped the evolution of life, including the emergence of humans. The Milankovitch cycles are more than just a scientific theory. They are a key to the history of Earth itself. They explain why continents were sometimes buried under kilometers of ice, why sea levels dropped and rose dramatically, and why climates fluctuated so dramatically over geological time. They show that the Earth's climate is a symphony conducted by the subtle variations in orbital mechanics, with each cycle contributing a different note, harmonizing to produce the grand movements of glacial and interglacial periods that have defined the planet's recent history. The grandeur of Milankovitch cycles lies in their combination of simplicity and complexity. The cycles themselves, eccentricity, obliquity, and precession, are relatively straightforward changes in Earth's motion. Yet their consequences unfold over vast timescales, interacting with countless elements of the Earth system to produce the magnificent patterns of glaciation that have sculpted our world. Orbital eccentricity is one of the most fascinating and crucial aspects of how our planet experiences changes in climate over time. It is a concept rooted in astronomy and physics, yet its consequences are deeply felt in the rhythms of Earth's natural cycles, particularly in the alternation between warmer periods and icy ages. To understand orbital eccentricity fully, we first need to think about the path that Earth follows as it moves around the Sun. This path is not a perfect circle. Instead, Earth travels along an orbit that is slightly stretched, or elliptical. This means that at some points in its journey, Earth is a little closer to the Sun, and at other points, it is a little farther away. This stretching and changing of distance from the Sun is what scientists call orbital eccentricity. The degree to which Earth's orbit deviates from a perfect circle is measured by a number, known as the eccentricity value. If this number is 0, Earth's orbit would be a perfect circle. In reality, the eccentricity of Earth's orbit varies naturally over tens of thousands to hundreds of thousands of years. It can change from nearly circular, with an eccentricity close to 0, to a more elongated shape, with an eccentricity approaching about 0.06. These numbers may seem small, but they are enough to create meaningful differences in how much solar energy reaches different parts of our planet during the course of a year. In other words, the shape of Earth's orbit directly influences the amount of sunlight that Earth receives, which then affects temperatures, ice sheets, ocean currents, and even the climate patterns that govern life all over the planet. When the orbit is more circular, the difference between the distance from the Sun at the closest point, called perihelion, and the farthest point, called aphelion, is minimal. This means that throughout the year, Earth receives a relatively steady amount of solar energy. On the other hand, when the orbit is more elongated, the difference between perihelion and aphelion becomes more pronounced. During perihelion, Earth is closer to the Sun, and the sunlight is slightly more intense, while at aphelion, Earth is farther away, and the sunlight is weaker. These variations in the distribution of sunlight are small on a day-to-day scale, but over thousands of years, they accumulate and have a significant impact on long-term climate patterns. This slow rhythm of change is one of the reasons why Earth has experienced repeated cycles of glaciation, known as ice ages, and warmer interglacial periods. Orbital eccentricity does not act alone. It interacts with two other related cycles of Earth's motion called obliquity and precession. Obliquity refers to the tilt of Earth's axis, and precession refers to the wobble of that axis as Earth spins. Together with eccentricity, these cycles are part of what scientists call the Milankovitch cycles, named after the Serbian mathematician and astronomer Milutin Milankovitch, who in the early 20th century studied how changes in Earth's orbit could drive ice ages. Eccentricity, with its very long cycles of about 100,000 years and 400,000 years, sets the stage for the other cycles to influence the climate more strongly. When eccentricity is high, meaning the orbit is more elliptical, the effects of obliquity and precession on sunlight distribution become amplified. When eccentricity is low, the orbit is more circular, and the effects of the other cycles are muted. Therefore, the shape of Earth's orbit acts as a kind of amplifier for long-term climate changes. The impact of orbital eccentricity on solar energy can be understood more clearly if we consider how sunlight is distributed across the planet's surface. The total amount of solar energy received by Earth over a year is called insolation. When the orbit is nearly circular, the distribution of insolation between the northern and southern hemispheres is relatively balanced. However, when the orbit becomes more elongated, insolation is unevenly distributed. This means that one hemisphere may receive more energy during its summer, while the other hemisphere receives less during its summer. This imbalance can influence the growth or melting of ice sheets, particularly in high-latitude regions such as Greenland and Antarctica. For instance, if the northern hemisphere experiences a summer when Earth is at aphelion, the sunlight is slightly weaker, and snow and ice are more likely to persist. Over thousands of years, this persistence of ice can contribute to the expansion of glaciers and ice sheets, which then affect global sea levels and climate. To put these effects into perspective, we can look at evidence from past ice ages. Scientists study ice cores, sediment layers, and fossil records to understand how climate has changed over hundreds of thousands of years. These records show that periods of high orbital eccentricity often coincide with more pronounced glacial cycles. For example, over the last 1 million years, the Earth has experienced glacial and interglacial cycles roughly every 100,000 years, a pattern that closely matches the long-term cycle of eccentricity. When eccentricity reaches higher values, the difference between perihelion and aphelion is larger, and the seasonal contrast between summer and winter in each hemisphere is amplified. This amplification, combined with changes in axial tilt and precession, can trigger the advance or retreat of ice sheets. It is important to emphasize that eccentricity does not create ice ages by itself. The changes in solar energy caused by eccentricity are relatively small, usually amounting to a difference of just a few percent in total annual insolation. However, the climate system is highly sensitive, and even small changes in sunlight can trigger feedback mechanisms that have a much larger effect. For instance, when ice sheets expand, they reflect more sunlight back into space, which leads to further cooling. Conversely, when ice sheets melt, the darker surfaces of land and ocean absorb more heat, leading to warming. These feedback loops, combined with the slow rhythm of eccentricity, obliquity, and precession, are what drive the grand cycles of ice ages and warmer periods that have shaped Earth's climate for millions of years. Orbital eccentricity also has implications beyond just ice ages. It influences the timing and intensity of monsoons, the productivity of ecosystems, and the circulation of ocean currents. When eccentricity is high, the differences in solar energy between seasons can alter rainfall patterns, affect plant growth, and change the habitats of animals. In some periods of Earth's history, these changes were so significant that they contributed to mass extinctions or the spread of certain species. For example, during periods of high eccentricity, the northern hemisphere might experience harsher summers and milder winters, which could affect the survival of both plants and animals that are adapted to specific seasonal patterns. Conversely, during periods of low eccentricity, seasonal contrasts are weaker and the climate is more stable, which can allow ecosystems to flourish in more predictable ways. Scientists have developed sophisticated models to simulate the effects of eccentricity on climate over long timescales. These models take into account not only the shape of Earth's orbit, but also the tilt and wobble of the axis, the distribution of continents and oceans, and the feedback effects of ice, vegetation, and clouds. By running these models over hundreds of thousands of years, scientists can reproduce the timing of past glacial cycles and make predictions about future climate changes. The results of these models confirm that eccentricity plays a key role in pacing the ice ages and in shaping the long-term patterns of climate variability. One of the most remarkable aspects of orbital eccentricity is its predictability. Unlike sudden volcanic eruptions or asteroid impacts, the changes in eccentricity follow a regular and predictable pattern, dictated by the laws of celestial mechanics. This predictability allows scientists to look far back into Earth's past and understand how the slow dance of the planets has influenced our climate. It also provides a framework for understanding how subtle changes in Earth's orbit can have profound effects over geological timescales, influencing everything from the growth of glaciers to the evolution of life. Axial tilt, also known as obliquity, is one of the fundamental aspects of how our planet experiences climate and seasons. To truly understand its importance, we first need to imagine the Earth not as a perfect, upright spinning sphere, but as a globe that leans slightly as it spins around an invisible line called its axis. This axis is an imaginary line running through the North and South poles, around which the Earth completes one full rotation every 24 hours, giving us day and night. Unlike a perfectly upright globe, the Earth's axis is tilted, and this tilt changes very slowly over thousands of years. Today, the tilt is about 23 degrees and 27 minutes, but it has varied between 22 and 24 degrees over tens of thousands of years. This gradual wobble and tilt is called obliquity, and it is a key factor that shapes the climate, the length and intensity of seasons, and even the advance and retreat of ice ages. The Earth's tilt determines how sunlight spreads across the planet. When the axis tilts more toward the sun's rays strike certain regions more directly, making summers warmer and winters milder in those areas. Conversely, when the tilt is smaller, the sun's rays spread more evenly across the planet, resulting in less extreme seasonal differences. This is important because the amount of solar energy reaching the surface drives temperature, weather patterns, ice formation, and even ocean currents. It might seem subtle, but a change of just a few degrees in axial tilt can make a tremendous difference over centuries and millennia. For example, a tilt closer to 24 degrees increases the contrast between summer and winter. Summers become hotter and winters colder, which can accelerate the melting of ice in summer and the growth of ice in winter, depending on where you are on the planet. When the tilt decreases toward 22 degrees, seasons become milder, with less dramatic swings between summer and winter temperatures, which can favor the buildup of ice sheets over long periods. This slow, rhythmic change in tilt is one of the natural clocks of the Earth's climate system, operating silently over tens of thousands of years, shaping the history of ice ages and warmer interglacial periods. Axial tilt is not constant because the Earth does not move in isolation. It is influenced by the gravitational pull of the Moon, the Sun, and the other planets in the solar system, especially the massive planets like Jupiter and Saturn. These gravitational forces nudge and pull the Earth gently, causing its tilt to oscillate in a cycle lasting roughly 41,000 years. This cycle is part of a larger set of patterns known as Milankovitch cycles, named after the Serbian mathematician Milutin Milankovitch, who first described how changes in Earth's orbit and tilt affect climate. The obliquity cycle is particularly important for its role in determining how much solar energy reaches the high latitudes near the poles. The polar regions are sensitive because ice and snow reflect sunlight, a phenomenon called the albedo effect. When sunlight is less direct due to a smaller tilt, summers are cooler in the polar regions, allowing snow and ice to accumulate year after year. Over thousands of years, this buildup can lead to the expansion of massive ice sheets that cover large portions of continents, initiating glacial periods. Conversely, when the tilt increases, polar summers become warmer, ice melts more rapidly, and the planet moves toward warmer interglacial conditions. In this way, axial tilt serves as a long-term thermostat, gradually controlling the rise and fall of ice across the Earth's surface. To understand the role of axial tilt more vividly, we can look at the record preserved in ice cores, sediment layers, and fossil evidence. Scientists studying these natural archives have found that periods of glaciation often correspond closely to times when the Earth's tilt was smaller, leading to weaker summers in polar regions and the slow buildup of ice sheets. When the tilt increased, the planet experienced warmer summers that melted ice and brought about periods of relative warmth. These changes are not abrupt. They unfold over tens of thousands of years, demonstrating the patience of natural processes. For example, the last major ice age, which peaked around 20,000 years ago, was influenced in part by a relatively small axial tilt, which allowed ice to persist and expand in the northern hemisphere. As the tilt gradually increased over the following millennia, ice sheets melted, sea levels rose, and the Earth transitioned into the warmer Holocene epoch, which we live in today. This delicate balance between tilt, solar energy, and ice shows how interconnected the components of the Earth system are, with obliquity serving as one of the master levers controlling climate on a grand timescale. Axial tilt also influences climate by affecting the distribution of sunlight across different latitudes. When the tilt is larger, mid-latitude regions, roughly between 30 and 60 degrees north and south, experience stronger seasonal contrasts. Summers become more intense, promoting faster plant growth, longer growing seasons, and increased evaporation, which can affect rainfall patterns. Winters become harsher, allowing snow to cover the ground for longer periods, influencing soil, vegetation, and water storage. This pattern repeats with each tilt cycle, shifting over tens of thousands of years and subtly altering the landscapes of continents. Areas that were once fertile may become drier or colder, and regions that were icy may thaw, creating new environments for plants and animals to adapt. The interplay between axial tilt and climate is therefore not just a matter of temperature, but also of ecological balance, influencing migration, evolution, and even human development over prehistoric timescales. Furthermore, axial tilt does not operate alone. It interacts with other elements of Earth's orbital mechanics, such as eccentricity, the shape of the Earth's orbit around the Sun, and precession, the slow wobble of the Earth's axis like a spinning top. Together, these factors create complex patterns in the amount and timing of solar radiation received at different latitudes, especially near the poles. For example, during periods when the tilt is larger and the Earth is closer to the Sun during northern summer, the high northern latitudes experience particularly warm summers, accelerating ice melt. Conversely, if the tilt is smaller and northern summer coincides with the Earth being farther from the Sun, ice can accumulate more easily, reinforcing glacial periods. This combination of tilt, orbit shape, and axial wobble produces intricate rhythms in climate, which have left clear signatures in geological and fossil records spanning millions of years. Obliquity has also influenced human history and the development of civilizations. As tilt-driven climate patterns shaped the growth and retreat of ice sheets, they altered sea levels, river flows, and vegetation zones. For early humans, these changes meant adapting to shifting resources and migration routes. During periods of larger tilt and warmer summers, northern areas became more habitable, allowing human populations to expand into new territories. During smaller tilt and colder summers, ice covered much of Europe and North America, forcing humans to cluster in more temperate regions and adapt their survival strategies. Archaeologists studying prehistoric settlements have found evidence that human communities often thrived or struggled depending on the long-term climate conditions driven by these orbital cycles. Obliquity, therefore, was not just a distant astronomical curiosity, but a subtle yet profound force, shaping the environment in which humans evolved and developed early technologies. Another important aspect of axial tilt is its influence on the oceans and the global climate system. Changes in tilt affect not only the surface temperature of the land, but also the amount of solar energy absorbed by the oceans. Warmer summers increase evaporation, which contributes to rainfall patterns and the circulation of air and water. Cooler summers reduce evaporation, allowing ice to persist and freshwater to accumulate in ice sheets. This freshwater can then flow into the oceans during melting periods, influencing ocean currents, sea level, and even climate patterns in distant regions. For example, the melting of large ice sheets after the last ice age, driven by a gradually increasing axial tilt, contributed to the rise of sea levels that flooded coastal areas and reshaped continents. It also affected ocean currents, such as the Gulf Stream in the Atlantic, with impacts that rippled across the globe, influencing climate far from the poles. In this way, obliquity links the heavens with the oceans, connecting the tilt of the Earth to the pulse of water across the planet. The study of axial tilt also highlights the predictability of natural climate rhythms. While human-caused climate change is rapid and unprecedented in its speed, the cycles of obliquity unfold over tens of thousands of years, providing a slow, measurable pattern that can be studied through paleoclimate data. Ice cores drilled from Greenland and Antarctica, for example, contain layers of snow and ice deposited year after year, each capturing chemical signatures of temperature, atmospheric composition, and sunlight intensity. By analyzing these layers, scientists can reconstruct past climate conditions and correlate them with known cycles of axial tilt. This research has revealed remarkable patterns. When the tilt was near its maximum of about 24 degrees, interglacial periods were more pronounced, while smaller tilts near 22 degrees coincided with the slow advance of ice sheets and glacial periods. These findings help us understand how the Earth's climate system responds to natural forces, providing a framework to study modern changes in comparison to historical cycles. Axial tilt also affects the length of seasons, which has practical consequences for ecosystems and human activity. A larger tilt amplifies the difference between summer and winter, making summers longer and warmer and winters colder and longer, particularly in higher latitudes. This impacts growing seasons for plants, the timing of animal migrations, and the availability of resources. In contrast, a smaller tilt reduces the contrast between seasons, producing milder summers and winters, which can allow ice to persist and build over time. Over tens of thousands of years, these shifts in seasonal intensity create long-term patterns in vegetation, soil development, and the distribution of species, demonstrating the profound influence of axial tilt on life itself. Even small variations in tilt can ripple through ecosystems, subtly changing which plants thrive, which animals migrate, and where water is stored in rivers, lakes, and ice sheets. In addition, axial tilt affects the distribution of energy across the planet's surface in ways that are amplified by feedback mechanisms. For instance, ice and snow reflect sunlight, which helps keep the poles cooler. When the tilt decreases and polar summers are less intense, snow persists longer, reinforcing cooling. Conversely, when the tilt increases, polar summers are stronger, ice melts faster, and darker land or water surfaces absorb more sunlight, further warming the region. These feedback loops can magnify the effect of small changes in tilt, creating larger impacts on global climate. Scientists studying these patterns have noted that obliquity-driven changes often act in concert with other natural cycles, such as variations in greenhouse gas concentrations, volcanic activity, and ocean circulation, producing complex but understandable patterns in Earth's climate history. Modern climate studies also consider axial tilt when modeling past and future climate scenarios. By understanding the timing and magnitude of tilt changes, scientists can simulate how ice sheets grew and melted in the past, how sea levels responded, and how ecosystems adapted. This knowledge allows for better predictions of how the Earth might react to rapid human-induced climate change by comparing it to slower, natural orbital cycles. While obliquity operates over tens of thousands of years, human activity can produce dramatic changes in mere centuries. Yet the natural cycles provide context, showing that Earth's climate system is highly sensitive to both slow astronomical forces and rapid changes from human influence. The influence of axial tilt extends even to regions far from the poles. In the tropics, the effect of tilt is less dramatic because sunlight is always relatively direct, but seasonal shifts in rainfall and monsoon patterns can still be affected by the tilt-driven changes in global circulation. In mid-latitudes, the impact is more pronounced, affecting temperature, precipitation, and storm patterns. This means that the cycles of obliquity not only shape ice sheets and polar climates, but also influence the everyday weather and climate that humans, animals, and plants experience around the globe. The precession of the equinoxes is a subtle but profoundly important astronomical phenomenon that has quietly influenced the cycles of life, climate, and human understanding for thousands of years. It is a slow, gradual wobble in the orientation of Earth's rotational axis. Imagine Earth not just spinning like a top, but the axis itself slowly tracing a circle in space. This wobble is caused by the gravitational pulls of the Sun and the Moon acting on Earth's slightly bulging equator, and it occurs over such a long period that it is almost imperceptible to humans living within a single lifetime. The complete cycle of this wobble takes roughly 26,000 years, a time span so vast that civilizations rise and fall many times before the cycle is even half complete. Yet, despite its slow pace, the precession of the equinoxes plays a crucial role in shaping the rhythms of the seasons and the broader patterns of Earth's climate. To understand precession, it helps to first imagine the Earth as a spinning top. As a top spins, it tends to wobble due to forces acting upon it. Similarly, Earth spins on its axis, tilted at an angle of approximately 23 degrees and 26 minutes. This tilt, known as obliquity, is responsible for the changing seasons. But because Earth is not a perfect sphere, it is slightly flattened at the poles and bulging at the equator. Gravitational forces from the Sun and the Moon exert a twisting effect on this tilted axis. Over centuries, this twisting causes the axis to slowly trace a circular path in space, like a slowly turning carousel. The direction that the North Pole points in the sky changes over time, tracing out a circle among the stars, and this gradual shift is the essence of precession. One of the most striking consequences of this phenomenon is the shift of the equinoxes. The equinoxes are the points in the year when day and night are of equal length, occurring around March 21st and September 23rd. Due to precession, these points slowly move westward along Earth's orbit, at a rate of approximately 50 seconds of arc per year, completing a full circuit of the zodiac in roughly 26,000 years. This means that the position of the sun during the equinoxes slowly shifts relative to the background stars. Over thousands of years, the constellations that were once aligned with the equinoxes are no longer in the same positions. Ancient astronomers, such as the Greek mathematician and astronomer Hipparchus, who lived around 190 to 128 years before the Common Era, were among the first to notice this gradual change. He compared his own careful observations of the stars with older Babylonian records and found that the positions of the equinoxes had shifted, marking the discovery of precession. This gradual movement of the equinoxes has profound implications for seasonal variations on Earth. Seasons are determined by the tilt of Earth's axis relative to its orbit around the Sun, and as precession alters the orientation of that tilt, it changes the timing of when each hemisphere experiences summer and winter. For example, currently, the northern hemisphere experiences its summer when Earth is farthest from the Sun, near aphelion, which occurs around early July. The southern hemisphere, on the other hand, has its summer near perihelion, when Earth is closest to the Sun, around early January. Over thousands of years, precession slowly shifts these points, meaning that the timing of the warmest and coldest seasons gradually changes relative to Earth's orbit. In a few thousand years, the northern hemisphere's summer will occur when Earth is closest to the Sun, making summers slightly warmer and winters slightly colder than they are today. The precession of the equinoxes does not act in isolation. It interacts with other long-term changes in Earth's orbit, known collectively as Milankovitch cycles. These include variations in orbital eccentricity, which is the shape of Earth's orbit around the Sun, and changes in obliquity, the tilt of Earth's axis. Together, these cycles produce complex patterns of solar radiation reaching Earth at different latitudes and during different seasons. Precession specifically affects the contrast between seasons. It determines whether the northern hemisphere experiences summer when Earth is closest to the Sun or farthest from it. This contrast can influence glacial and interglacial periods. When summers are cooler in the high northern latitudes, snow and ice can accumulate, potentially triggering the advance of glaciers over millennia. Conversely, warmer summers can lead to melting and the retreat of ice sheets. Precession also plays a subtle role in the distribution of sunlight across the globe. The effect is more pronounced at higher latitudes because these regions experience greater seasonal differences. For instance, during times when precession aligns the northern hemisphere's summer with Earth's perihelion, the hemisphere receives slightly more solar energy in summer and slightly less in winter. This amplification of seasonal extremes can have long-term effects on climate patterns, influencing not only ice sheets but also atmospheric circulation, ocean currents, and monsoons. Scientists studying paleoclimate often use precession as one of the key factors in reconstructing ancient climates, relying on evidence such as ocean sediments, ice cores, and tree rings to track how changes in Earth's orientation have shaped the environment over tens of thousands of years. Ancient civilizations also recognized the effects of precession, even if they did not fully understand the mechanics behind it. In many cultures, calendars were closely tied to the movements of the sun, moon, and stars. The gradual shift of the equinoxes meant that over centuries, seasonal markers would drift relative to the stars. For example, the timing of solstices and equinoxes relative to certain constellations would change slowly over generations. This likely influenced agricultural practices, ritual calendars, and even mythology. Some researchers have suggested that ancient structures, such as Stonehenge in England or the pyramids of Giza in Egypt, may have been aligned with particular celestial events, taking into account the slow drift caused by precession, demonstrating the long-term awareness of these cycles. Precession also affects the timing of climatic phenomena known as monsoons, which are seasonal winds that bring heavy rains to certain regions. The strength and timing of monsoons are influenced by the contrast between land and ocean temperatures, which in turn are affected by the seasonal distribution of sunlight. As precession shifts the timing of the equinoxes and solstices relative to Earth's orbit, it changes the pattern of solar heating across continents and oceans. Over thousands of years, this can alter the intensity and duration of monsoon seasons, affecting ecosystems and human civilizations alike. Ancient societies that depended on predictable monsoon rains for agriculture would have had to adapt gradually to these slow changes, perhaps by shifting planting seasons or developing storage methods for food. The study of precession and its effects has been greatly enhanced by modern technology. Telescopes, satellites, and precise astronomical instruments allow scientists to measure the position of stars and the orientation of Earth's axis with extraordinary accuracy. Computer models now simulate the interactions between precession, eccentricity, and obliquity, helping researchers predict long-term climate trends and understand past changes. For example, models indicate that the northern hemisphere will experience increasingly warmer summers when precession aligns summer with perihelion over the next several thousand years, influencing the potential growth or decline of glaciers. Similarly, the southern hemisphere's climate will experience complementary shifts, with summer and winter extremes gradually changing in strength. Precession also leaves a mark in the geological and biological record. Layers of sediment in oceans and lakes often contain tiny fossils and chemical signatures that reflect past temperatures and seasonal variations. By examining these layers, scientists can detect cyclical patterns that correspond to precessional cycles. For instance, variations in the abundance of certain microorganisms in marine sediments can indicate changes in seasonal sunlight, while isotopic ratios of oxygen in ice cores can reveal shifts in temperature and precipitation. These natural archives provide a window into Earth's climate history, allowing us to see how precession has influenced environmental changes over tens of thousands of years. The effect of precession on seasonal variations extends even to the timing of the equinoxes themselves. Because precession gradually moves the equinoxes along Earth's orbit, the dates on which they occur can slowly shift over millennia. While the change is imperceptible on a human timescale, over thousands of years, the equinoxes can occur several days earlier or later relative to the calendar year. This phenomenon is one reason why ancient calendars eventually required correction. For example, the Julian calendar, introduced by Julius Caesar in 45 years before the Common Era, did not perfectly account for the slow drift of equinoxes caused by precession, leading to a gradual misalignment of seasonal dates. The later introduction of the Gregorian calendar in 1582 corrected this drift, demonstrating how awareness of precessional effects has practical implications even for human timekeeping. Astronomically, precession also changes the apparent position of the North Star over millennia. Currently, Polaris serves as the North Star, lying nearly along Earth's axis of rotation. However, due to precession, this alignment is temporary on cosmic timescales. In approximately 12,000 years, the bright star Vega will become the North Star, while Polaris will gradually move away from the pole. This shifting of the celestial pole does not affect daily life in a direct way, but it illustrates the slow and continuous nature of precession and its impact on our orientation relative to the cosmos. Precession has inspired both scientific inquiry and cultural reflection throughout history. Ancient astronomers tracked the stars to understand seasonal changes and navigation, while later scholars, including the likes of Claudius Ptolemy in the 2nd century Common Era, studied precession to refine astronomical models. Observations of precession also played a role in the development of celestial mechanics, the branch of science that explains the motions of celestial bodies under the influence of gravity. Understanding precession was crucial for the work of later scientists, such as Johannes Kepler in the 17th century and Isaac Newton, whose laws of motion and gravitation provided the framework for explaining why Earth wobbles on its axis. The influence of precession is subtle but cumulative. On human timescales, the wobble is imperceptible. A single lifetime might see no noticeable change. Yet over thousands of years, precession affects the intensity of seasons, the growth and retreat of glaciers, the timing of monsoons, and even the alignment of celestial landmarks. Its slow, rhythmic motion connects the seemingly constant patterns of day and night with the immense cycles of the cosmos. In addition, precession has indirect effects on ecosystems and biodiversity. Seasonal changes dictated by precession influence the timing of plant flowering, animal migration, and reproductive cycles. Over long timescales, shifts in the timing and intensity of seasons can alter habitats, forcing species to adapt, migrate, or face extinction. For example, gradual increases in summer heat due to precessional alignment could influence forest growth, ice cover, and ocean currents, reshaping the environment and the life it supports. In this sense, precession is not merely an astronomical curiosity, It is a driver of ecological change and a silent architect of Earth's natural rhythms. Furthermore, precession has a role in the study of paleoclimatology, the science of ancient climates. By examining how precessional cycles align with patterns in sediment cores, scientists can understand the timing of ice ages and interglacial periods. These studies reveal that precession often works in concert with other Milankovitch cycles to create complex, long-term climate oscillations. For example, ice ages do not begin or end due to precession alone, but precession can amplify or dampen seasonal contrasts, influencing whether ice sheets grow or melt. This understanding allows researchers to connect astronomical cycles with tangible changes in Earth's environment over hundreds of thousands of years. The human fascination with precession also extends to its philosophical and cultural implications. The realization that Earth itself moves in such a slow and predictable cycle over tens of thousands of years offers a humbling perspective on our place in the universe. Civilizations that observed the stars could see patterns that outlasted generations, inspiring myths, calendars, and rituals connected to the heavens. Even today, modern science continues this tradition, linking ancient observations with precise measurements and sophisticated models that reveal the grand cycles of time and space. Earth's climate is shaped by a complex interplay of factors, and among the most powerful of these are greenhouse gases, which have a profound influence on the rise and fall of ice sheets over thousands of years. These gases, including carbon dioxide, methane, and water vapor, have the ability to trap heat in the atmosphere, acting like an invisible blanket around the planet. This trapping of heat is crucial because it amplifies the subtle changes in solar energy that drive glacial cycles, making cold periods colder and warm periods warmer. Without greenhouse gases, the small variations in Earth's orbit and tilt that naturally affect climate would be far less effective at causing ice ages or glacial retreats, and the planet's climate would remain more uniform. Carbon dioxide, one of the most well-known greenhouse gases, is released into the atmosphere through volcanic eruptions, the decay of organic material, and more recently through human activity such as burning fossil fuels. Even before humans began altering the atmosphere on a large scale, carbon dioxide levels fluctuated naturally. These fluctuations were closely linked to glacial cycles. During periods when ice sheets expanded, carbon dioxide concentrations tended to drop. Cooler oceans absorbed more CO2 from the atmosphere, creating a feedback loop. Lower CO2 led to cooler temperatures, which allowed ice sheets to grow further, which in turn absorbed even more CO2. Conversely, when the climate began to warm and ice sheets retreated, carbon dioxide was released back into the atmosphere from the oceans, amplifying the warming and accelerating the melting of ice. This delicate balance demonstrates that carbon dioxide does not merely respond to climate changes. It actively strengthens them, making glacial and interglacial transitions more pronounced. Methane, although present in much smaller amounts than carbon dioxide, is an extremely potent greenhouse gas, capable of trapping heat more efficiently on a molecule-by-molecule basis. Methane is released from wetlands, permafrost, and even the digestive processes of large animals. During cold periods, methane concentrations were lower, contributing to cooler temperatures. As the planet warmed and ice sheets shrank, thawing permafrost and expanding wetlands released methane into the atmosphere, reinforcing warming trends. Water vapor, though highly variable and dependent on temperature, also acts as a multiplier for these effects. As the air warms, it can hold more water vapor, which in turn traps more heat and further amplifies the warming initiated by carbon dioxide and methane. In this way, greenhouse gases act not only as drivers of climate, but as magnifiers, turning small changes into dramatic shifts in global temperatures and ice cover. The influence of greenhouse gases on glacial cycles is intertwined with changes in Earth's orbit and tilt, known as Milankovitch cycles. These cycles affect how sunlight is distributed across the planet, creating subtle differences in seasonal intensity and duration. For example, when northern hemisphere summers receive slightly less sunlight, ice sheets can grow because winter snowfall does not completely melt during the warmer months. On their own, these orbital variations might produce only minor cooling or warming, but when greenhouse gas feedbacks are included, the effects are amplified. A slight reduction in solar energy during summer can lead to more ice growth, which reduces atmospheric CO2 by increasing ocean absorption. The lower CO2 then cools the climate further, allowing ice sheets to expand more quickly and reinforcing the cycle. Conversely, when orbital changes favor warming, the release of greenhouse gases enhances ice melting, causing rapid retreats of ice sheets and triggering interglacial periods of warmth. Without the amplifying effect of greenhouse gases, these orbital changes would produce much weaker climate shifts, and ice ages might not have occurred with the intensity seen in Earth's recent history. Evidence for the role of greenhouse gases in glacial cycles comes from ice cores drilled from Greenland, Antarctica, and other regions with deep, long-lasting ice sheets. These cores preserve tiny bubbles of ancient air, allowing scientists to measure past concentrations of carbon dioxide, methane, and other gases with remarkable precision. Analyses of ice cores covering hundreds of thousands of years reveal a clear pattern. Concentrations of CO2 and methane rise and fall in close synchrony with temperature changes and ice volume. During the last major glacial period, which reached its peak around 20,000 years ago, CO2 levels were around 180 parts per million, much lower than today's levels of over 420 parts per million. As the planet moved into the current interglacial period, known as the Holocene, CO2 concentrations increased, contributing to global warming and the melting of massive ice sheets. Methane showed a similar pattern, rising from roughly 400 parts per billion during the glacial maximum to nearly 800 parts per billion as ice sheets retreated. These records demonstrate that greenhouse gases were not passive bystanders, but active participants in shaping Earth's climate over glacial interglacial timescales. The interactions between greenhouse gases and ice sheets are also evident in the feedback loops that govern climate stability. One critical feedback involves albedo, or the reflectivity of Earth's surface. Ice and snow reflect sunlight back into space, helping to keep the planet cool. When ice sheets expand, more sunlight is reflected, reinforcing cooling. As greenhouse gases decline during these periods, the cooling effect is magnified, allowing ice to grow even further. Conversely, when ice sheets melt, darker surfaces such as oceans or land absorb more sunlight, accelerating warming. Rising greenhouse gas concentrations during these periods strengthen the effect, promoting faster ice retreat and warmer climates. This combination of albedo and greenhouse gas feedbacks illustrates the interconnected nature of Earth's climate system, where changes in one component can trigger cascading effects throughout the planet's environment. Ocean circulation also plays a key role in linking greenhouse gases to glacial cycles. During glacial periods, colder ocean temperatures and expanded ice sheets alter the movement of currents, affecting the distribution of heat and nutrients around the globe. These changes influence how much carbon dioxide the oceans can absorb or release. Colder oceans are more efficient at absorbing CO2 from the atmosphere, reducing greenhouse gas levels and promoting further cooling. When warming begins, ocean circulation shifts, releasing stored CO2 and methane back into the atmosphere and enhancing warming trends. This dynamic demonstrates that ice sheets, oceans, and greenhouse gases are deeply interconnected, each influencing the others in ways that amplify the natural cycles of glacial advance and retreat. The timing of these feedbacks is also essential for understanding glacial cycles. Changes in greenhouse gas concentrations do not occur instantaneously. They unfold over hundreds to thousands of years, in step with slow changes in ice volume and ocean chemistry. This gradual response allows greenhouse gases to reinforce climatic trends initiated by orbital variations without completely dominating the cycle. For example, a reduction in solar radiation may initially trigger ice growth, but the subsequent decline in CO2 over centuries ensures that cooling continues and ice sheets expand further. Similarly, once warming begins, the slow release of greenhouse gases ensures that ice retreat accelerates, creating the characteristic sharp transitions from glacial to interglacial conditions observed in the geologic record. These timescales highlight the importance of greenhouse gases as stabilizers and amplifiers of long-term climate patterns. The influence of greenhouse gases extends beyond temperature alone. They also affect precipitation patterns, wind systems, and the distribution of vegetation, all of which interact with ice sheets. During glacial periods, lower CO2 and colder temperatures reduce evaporation, leading to drier conditions in some regions. Ice sheets grow more easily under these conditions because less snow melts during the summer. When CO2 rises and the climate warms, evaporation increases, precipitation patterns shift, and vegetation expands into areas previously covered by ice, further reinforcing the retreat of glaciers. These interconnected effects illustrate the complex, multidimensional role of greenhouse gases in shaping not just temperature, but the broader environment in which ice sheets exist. The study of past glacial cycles also offers insight into the potential consequences of modern changes in greenhouse gas concentrations. Today, human activities have dramatically increased CO2, methane, and other greenhouse gases, pushing atmospheric concentrations far above the natural ranges seen over the past hundreds of thousands of years. By understanding how small natural variations in greenhouse gases once amplified glacial cycles, scientists can better appreciate the scale and speed at which current climate change is occurring. The unprecedented rate of increase in greenhouse gases today has the potential to produce changes in ice sheets, sea levels, and global climate far faster than any natural cycle, highlighting the critical role of these gases in shaping Earth's climate, both in the past and in the present. In addition to carbon dioxide and methane, other greenhouse gases such as nitrous oxide, though less abundant, also contribute to climate amplification during glacial cycles. Nitrous oxide, produced by microbial activity in soils and oceans, has a long atmospheric lifetime and significant heat-trapping ability. Its variations over glacial-interglacial timescales, recorded in ice cores, show a close relationship with temperature and ice volume, reinforcing the multi-gas feedback system that amplifies climate changes. Even seemingly minor gases play a role in this intricate system, demonstrating that glacial cycles are the product of many interacting components, all influenced by the greenhouse effect. Greenhouse gases do not act alone, of course. They operate within a web of interactions that includes Earth's orbit, solar energy, volcanic activity, ocean currents, and ice sheet dynamics. Yet their role as amplifiers is essential. Orbital variations can initiate small shifts in climate, but without the feedback from greenhouse gases, these shifts would be muted, failing to produce the large-scale glaciations and interglacial warmth observed over the last million years. By enhancing the effects of solar forcing, greenhouse gases help create the rhythmic pattern of cold and warm periods that characterize Earth's recent geologic history. They act as both accelerators and moderators, ensuring that ice sheets grow and melt in ways that are dramatic, predictable, and interconnected with other components of the Earth system. The importance of greenhouse gases in glacial cycles is further confirmed by climate models that simulate past climates using physical laws and empirical data. These models show that removing greenhouse gas feedbacks produces a world where ice sheets respond only weakly to orbital changes. With greenhouse gas feedbacks included, the timing and magnitude of glacial and interglacial periods closely match the geologic record, providing strong evidence that these gases are critical amplifiers of climate change. Such models also illustrate the complexity of the system, revealing how small shifts in CO2 or methane can trigger cascading effects on ice sheets, ocean circulation, and global temperatures over thousands of years. Finally, the story of greenhouse gases in glacial cycles is a story of balance and feedback, of delicate forces acting over immense timescales. They demonstrate that Earth's climate is not determined by any single factor, but by the interactions of many systems, each influencing the others in subtle and profound ways. Carbon dioxide, methane, water vapor, and other gases are not merely passive components of the atmosphere. They are active agents, capable of amplifying or damping climate trends, of accelerating the growth or retreat of ice sheets, and of shaping the world in ways that are visible in the fossil record, the structure of ice sheets, and the chemical composition of ancient air preserved in ice cores. By studying these interactions, scientists gain insight not only into the rhythms of the past, but also into the potential trajectories of Earth's future climate. The same gases that once amplified glacial cycles now play a central role in human-driven climate change, highlighting the continuity of processes that operate over tens of thousands of years. Understanding how greenhouse gases amplified ice ages helps us understand the mechanisms that could accelerate warming today, the potential for ice sheet instability, and the long-term consequences for sea level, ecosystems, and human societies. The history of glacial cycles, written in the language of greenhouse gases, ice, and ocean currents, reveals the extraordinary power of seemingly invisible molecules to shape the destiny of the entire planet, demonstrating that in the grand story of Earth's climate, nothing is small, and every part is connected in ways that are both intricate and awe-inspiring. Greenhouse gases, through their interplay with ice sheets, oceans, and sunlight, show us that the climate system is a tightly interwoven web of cause and effect. Even the tiniest shift in CO2 or methane can ripple across centuries, altering the balance of ice and water, cold and warmth, and life across the planet. This intricate connection between greenhouse gases and ice sheets also underscores the fragility and resilience of the Earth system. Ice sheets, which can weigh millions of tons and span thousands of kilometers, respond to forces that begin with tiny fluctuations in atmospheric chemistry. Carbon dioxide and methane, though invisible and minute in concentration compared to nitrogen and oxygen, hold the power to amplify these forces, creating dramatic glacial cycles and reshaping the climate over tens of thousands of years. Water vapor, acting as both a response and amplifier, ensures that these changes cascade through the system, reinforcing the effects of other greenhouse gases and magnifying the climatic consequences. The pattern of glacial cycles, recorded in ice cores, sediments, and ocean chemistry, repeatedly shows that greenhouse gases are indispensable actors in Earth's climate drama. Their changes precede or coincide with major ice sheet expansions and retreats, demonstrating their role as both triggers and accelerators. The combination of orbital variations, ice albedo feedback, ocean circulation, and greenhouse gas fluctuations creates the rhythm of ice ages, a rhythm that has persisted for hundreds of thousands of years. Without greenhouse gases, the swings between glacial and interglacial periods would be muted, and Earth's climate history would be far less dynamic, lacking the pronounced cycles that have defined the planet's recent geological era.